Why don't we get started? My name's Steve Castillo. I worked here for 22 years, retired, came back, and now I'm teaching a class. That's my role at New Mexico State in the electrical engineering department. But just briefly, I want to let you know how great riding bicycles is. Because one day I was riding a bicycle, and I was up at Dripping Springs on my bicycle, leaning over my bike, and an old colleague friend of mine, Donahue, was similarly gassed at the top of that climb. And we started talking, and he revealed that his daughter is an electrical engineer, and she was working on some really cool stuff at a university in Sweden. And so he put me in contact with her, and one thing led to another. She was visiting here in Las Cruces. She grew up here in Las Cruces, and she agreed to give a talk on her research at this time. So if you want good things to happen in your life, ride a bicycle. Okay?
Does it fall from a bicycle?
What's that?
Does it fall from a bicycle?
Well, I have a titanium hip because I fell off a bicycle. So with that, I'm going to turn it over to Professor Donahue.
Thanks so much, Steve. Yeah, thank you very much for being here. I wanted to tell the same story because I'm excited about how that went as well, and for the chance to come and talk to you guys. And I have my sister and brother and Tina and my baby even in the room still while he's behaving. So thank you for coming out. I will introduce myself a bit, but I wanted to see what the backgrounds are here. So I got to hear some about electrical engineering, computer engineering. I heard we might have some biologists in the room. Are there any? Chemists. Biochemists, okay. How about over here? Electrical engineering, engineers. Okay, so I mean, some of the work we do, it requires the expertise of a lot of different fields. Aw, his nap was badly timed. So, a little bit about myself first. I grew up in New Mexico. Usually if I'm introducing myself, especially abroad, I have to make sure people know where that is and that it's part of the United States, and maybe give a point of reference or something they know about. So the Manhattan Project and atomic bomb testing helps with that. In more recent years, Breaking Bad has been a big thing. So that helped make New Mexico more famous as well. Otherwise, I really like to give propaganda and advertisement for the nature and things like biking and seeing white sands. So it's one of the most spectacular places that I've still seen in the world. And yes, I did my high school, grew up here and went to high school here, and then I moved on to Texas Tech for university, and there I had my bachelor's studies. I got a bachelor's in both electrical engineering and one in computer science, and then went on with electrical engineering for my master's. And there I worked at Texas Instruments in the digital light processing department with these little micromirrors that are often in the projectors. So that was very interesting. Towards the end, I won a Fulbright scholarship to go over to Germany, and that was intended for 1 year, but then I hung around and did my Ph.D. work there. So that was on high electron mobility transistors. That's what these guys are. So it's the source and drain contacts in this direction, and the channel material in between, and there we were doing different functionalizations, looking for pH sensitivity or nitric oxide sensitivity, and to work in very low volumes. So one of the applications was fetal blood sampling, where you only have a few microliters of fluid to work with. So that was on 3.5 semiconductors. After that, I kind of entered the world of organic electronics in France at a postdoc. So I went there for a postdoc. Is there anyone working with organic electronics here? Polymers, polymer synthesis? None? Okay, I'll go into some of the properties of those and why we're interested in them for these electronic interfaces. On a more personal note, these younger two we moved to Germany with. They were 5 and about 1. And while we were in Germany, we added to the family 2 more boys. Once we moved on to France, so this is outside Marseille. It's very beautiful as well. They're the calanques or coves. It's green-blue water and white rock. So this is a hike down to one of these coves, and you can see the kids are growing up. So that's a very, very beautiful area if you get the chance to visit. And then we packed up from sunny France and moved up to Sweden. So this is approximately the location of Norrköping, where we have a campus of Linköping University. And there I'm at the Laboratory of Organic Electronics. So that's why I ask about organic electronics. Here we've made a couple more additions to the family. This one just left the room. These are some giant wolf dog shepherds and shepherd mixes. And this one will be coming soon. And then I guess we're done with that part. So that's the personal side. And, you know, I don't know how many students are here. I would just emphasize that you don't always have to wait for stability and think things are going to be perfect. We had a lot of fun moving around with our family and visiting all these countries. So in Sweden, I have secured some funding to kind of continue down the research line that I enjoy. The main one is this Vetenskapsrådet VR starting grant, and there's some associated co-funding and some from this Wallenberry Wood Science Center where they have emphasis on natural materials and wood-based materials. And with that, I support some of the work that we're now doing. So that has a basis on therapeutic neuromodulation. These are some more or less well-known examples of therapeutic neuromodulation, starting with deep brain stimulation. This was approved already in 1997, FDA approved for treatment of essential tremor and Parkinson's disease. Later, this was approved for dystonia and obsessive compulsive disorder, and these things are being studied to treat many disorders, of course, in the research world. Vagus nerve stimulation, similarly, was approved in 1997 for drug-resistant epilepsy, and later has been approved for cluster headaches and depression. And this one is also widely studied. I'll come back to it. It controls a lot of the signaling pathways within our body. Spinal cord stimulation for pain management, sacral nerve stimulation for urinary incontinence, and cochlear and retinal implants for restoration of hearing and sight, of course. So these interface with both the central and peripheral nervous system. Here, the central nervous system is shown in yellow. That encompasses our brain, brainstem, and spinal cord. And the peripheral nervous system is in blue, so that innervates the rest of our bodies, controlling all the sensory and motor pathways. And is interesting from a therapeutic and engineering standpoint as it's more accessible. So it's kind of like doorways that we can access and try to target specific bodily functions, whether we want to read signals out or influence those with this type of therapy. One of the earliest examples of this you see here in the top picture. So this is one of the first examples, or is first example of peripheral nerve interfacing. This was to control urinary incontinence. It was a very simple radio implant, looped wire device. You can see some little loops here. And although simple, it did its job of controlling muscle contractions, and the field has really progressed over the next 50, 60 years to the clinical state-of-the-art vagus nerve implant that you see here. So there's been a great deal of advancement in the materials and the technology, but these electrodes are still very large, very rudimentary. I'll show you a picture later if you want to look of an actual human surgery with this. They need a lot of mechanical reinforcement around the nerve, and it's extremely invasive. And of course, the cost and pain of surgery is a factor as well. So we want to improve on those materials. Also, this requires the wiring to the power supply, and this power supply is typically implanted in the chest and has to be changed out over time. So these are all complications of this type of device and approach. What's actually happening at the interface of those electrodes with the tissue is that usually some kind of current pulse that looks like this is being delivered. Slight variations on that are used as well, but it has some pulse amplitude, pulse duration. These two together give the charge that's delivered into the environment during that time. And we want to essentially mimic that, but without all the bulky equipment that goes with it. And these type of pulses are delivered with a specific frequency too, but I'll come back to that. So we're using two approaches that I'll talk about today to try and achieve that. One is based on optoelectronics, and this is minimally invasive, and one is completely non-invasive, where we have electrodes outside of the body, and I'll come to that secondly. So the first one are these little optoelectronic implants. So they're wireless. That is one of the big advantages. They are freestanding. They're also based on these types of materials. So I brought those with me. This is not one of those devices, but a few of the devices that I'll show you are based on the similar substrates and thin film deposition techniques. So they're very, maybe you can see it moving, very flexible. They conform to the skin, to the tissue, to the brain surface, depending on what the application is. So they're only a few micrometers thick. That's about 1/10 or even less of a human hair. Some of these are a bit torn already. They're just dummies. I'm adding some water to the Petri dish so that they'll delaminate easier. But if you're interested, I can pass them around maybe. So we base a lot of these devices on those type of substrates, and then they can also do things like wrap around what would be the nerve. This is just an image on a capillary that's a similar size to the intended nerve, which in the experiments I'll show you will be about 1 millimeter in diameter. So this is made up of a little PN junction that is here on a freestanding semi-transparent or transparent conductor on top of this polymer material that makes up the substrate. So this one has a locking mechanism, little teeth that are incorporated. It's like a zip tie. You can wrap it around the nerve and fix it at the best location. You can imagine these as little solar cells. They're absorbing light and separating charge and giving essentially a stimulation pulse at the interface. So this is just depicted with a cartoon cell membrane. This would be in contact with the nerve or whatever the target is for the specific experiment. The materials are shown here. So these are organic pigments or dyes. They're used in clothing, cosmetics, so they're non-toxic. And they're quite stable in this type of biological environment, so that's very important. It's tough to be in essentially seawater, have a lot of electronics there and keep stability. The way we characterize I should mention that they absorb most efficiently deep red light. So that is also great for bioelectronic applications because this wavelength of light best penetrates tissue without causing heating or other negative effects. The way we characterize them is in an electrolyte environment. So we give stimulation pulses or light pulses from the backside and measure just at the top side of this little pixel to know how much photocurrent or photovoltage we're inducing and what type of charge we can be expected to deliver. Here you see for different pixel sizes, the VT max, so that's based on this transient voltage that you see, the maximum value. And as you would expect for larger pixel sizes, we have a larger voltage that we achieve. So this was essentially sufficient to go ahead with the intended experiments. These ones are done with the sciatic nerve of a rat. So the sciatic nerve is often used to prototype devices. It's quite straightforward to see whether it's effective. You stimulate the nerve and you see a kick of the animal. In addition, you can quite easily measure the compound muscle action potentials and have some quantitative measurement of how efficient you're stimulating as well. So here you see, there will be a few photos of surgeries and these types of nerves. I hope that's okay. I'll try to warn you if any for the vagus nerve one, but here you see this is the compound muscle action potential, so just measuring in the muscle there beside the nerve. And you see this for the light pulse duration and for different intensities. So higher in intensity and longer light pulse gives you more charge and you expect a larger effect. So this was great. These are fully implanted. The surgery site closed up and this was carried out over multiple months. So that showed promising results for the stability. Again, this is often used for prototyping and maybe not there are other things that would be more useful for studying disease models and trying to understand chronic stimulation. So where we next wanted to move is looking into the mouse model and vagus nerve stimulation. So this is challenging in the sense that the mouse vagus nerve is only about 100 micrometers in diameter. So that's already 1/10 of the size or less of the sciatic nerve you just saw, or you still see here. And as with all electronics, as you try to miniaturize things, you face challenges. So here we We went into this planning to use the heart rate as a readout. The vagus nerve I didn't mention before. It's the longest of the 12 cranial nerves and innervates everything from the mouth and throat down to the heart and then down further through the gut and the colon. So it has really a lot of signaling pathways, which is why it has a lot of applications for therapy as well. But so here we will use the heart rate to directly have some readout of whether we're stimulating efficiently or not. On the other hand, for chronic experiments, we would use the left side for inflammation studies, and the mouse has some very well-developed disease models. So we needed to step back because of this miniaturization challenge and use some wired arrays before moving to the wireless devices. So here we developed some arrays that are very similar to what's being passed around now. So the thin film metal, the electrode coatings I'm going to tell you a little bit about. These were all designed to wrap exactly around the nerve and basically fully wrap it with these electrodes and have the array to choose different parameters and patterns. This is a little pulse oximeter that just is meant for small animal models, so that's what we can use to directly read the heart rate out. And yeah, again, this is a surgery photo. You can't really see. The device wraps around and laminates back on itself. This has good adhesion for these acute experiments. And the vagus nerve is so tiny, it's really hard to see. So the material here, I will just go through a couple details. This is P.PSS, which is quite well known if you're talking about organic electronics, and is very interesting for neural interfaces or a lot of biological interfaces actually, because this one conducts electrons. It's a conducting polymer, conducts electrons and ions. So as the body is made up of ions, this can be quite efficient for signal transduction between ions and electrons. And one thing that's good about it is that whereas in the case of inorganic semiconductors, so this is like a silicon lattice with the silicon oxide on top, here we're limited to the surface area, so the ions build up at the surface. We have the electrical double layer, whereas with these type of mixed electron ion conductors, the conducting polymers, you get to use essentially the bulk, the volume of the film. So that means when you want to miniaturize electrodes, you can still benefit from good signal recording and maintaining low voltages when you're stimulating, so that we would normally characterize with electrochemical impedance spectroscopy, where you look across the frequencies. Often 1 kilohertz is listed for the impedance here, since that's the frequency of the action potential. And here we want to have a low impedance that keeps a good signal to noise ratio when we're recording and low voltages when we're stimulating for therapeutic applications. So a large electrode would have low impedance here, but would not be specific for the target, either recording or stimulating. If we make the electrode very small, the impedance jumps up. I'm sorry, I see that the nano and micro labels are just switched. As we make the microelectrode very small so that we have specificity, there we have a much higher impedance, which is not good. The noise would be very high, or we need to have very high voltages, which can cause tissue damage. There are some structuring techniques that you can use that starts to bring this down, but these conducting polymers, where we can use the entire volume of the film, really help to bring it all the way back down or close to what you would have on a macro electrode with the benefit of the specificity. So these are all some different devices, again, similar to what I just passed around, that are based on very thin film materials and these electrode coatings. Okay, so that's what we use on these stimulation arrays. And then we played around with the parameters. So either the frequency, how often we're delivering these pulses, or the patterns. So the reason I said we developed this array was so we could use different patterns. In the end, maybe I didn't mention clearly, we want to redesign the photocapacitor, this optoelectronic device, to be the most efficient so that we can use it chronically in time. So here we have these kind of longitudinal side-by-side arrangements. This one is meant to mimic the original photocapacitor design, where this PN junction was kind of in the middle, surrounded by the back electrode. And then there's this transverse, which has basically no effect. It's almost like a control measurement. And this is what we explored. The experiments look something like this. So we have a baseline of the heart rate that you can see here. And Then during stimulation, which is the red line there, we see some drop if we're stimulating efficiently. And there we can use the difference and have a quantitative result to compare of the change from the baseline, the percentage change. So then we use that to compare the different results. So here you can see this one that was the original design is less efficient. So here we have heart rate reduction and the charge injected per phase. So that's again the pulse duration and the pulse amplitude together. So here the original design is not quite as efficient as these longitudinal designs. So that's good. We could then begin to redesign our wireless devices. We also learned that mice can be quite variable. Here we had some that were not responding almost at all, so they have very little heart rate reduction, even with some larger charge injection. Some that were extremely low threshold responders, but most of them were in this normal or medium response, so we could compare things pretty well. Here you have the frequency dependence, so the heart rate reduction based on the frequencies used, so how fast we're delivering the pulses. And there we see with higher frequency, there's more of an effect, which is known from literature, and this is more of a validation. So there we move to these photocapacitors, the optoelectronic wireless implants. And I won't talk much about that because they were still not efficient enough to stimulate anything except for these low threshold mice. So these guys here, we could have some effect, but otherwise it was not enough, and that's with the surgery site open before closing and carrying out. Yes?
Do you have an impedance mismatch between the device and the organ that you're interfacing with? Does that change? Does that vary across the human body?
Yes, I mean, it depends. Sometimes it's mainly, well, first of all, it depends on how close you can interface with the tissue. So normally you want to be in very close contact so there's not current leakage, so that you don't lose the effect, so that you have the best effect, let's say like that. But there is definitely, I mean, especially when you start talking about skull and bone and soft tissue, heart and nerves and stuff, yeah, it's definitely also a consideration. So some of the one I'll show after, it's from outside propagating inside, so then we really have to consider those different impedances. Yes. And it's often modeled as well, so that's a very good question. Yeah, so from here, like I say, I won't talk to, please feel free to ask questions as we go along. It's much, I meant to say that before, I'm glad you did it. So we moved into a kind of hybrid design. Instead of being exactly on the nerve with the PN junction, we call it the flag. The photovoltaic part is drawn out and away, which is good for two things. It's larger and can generate more charge, and also can be closer to the skin, so there's not as much attenuation as when you illuminate with light. And then these are again coated with this conducting polymer, and that's the part that wraps around the nerve. So with this we had very efficient stimulation, sometimes really large values that are certainly not needed for therapeutic applications. In fact, no heart rate modulation is needed. That's just kind of the limit to know that you're having an effect, and then you would want to stay beneath that. So here you see heart rate drop with brightness. These are quite low brightnesses. We can go up to 100 as you see here. And then this is color-coded with frequency again, the same trend, and with two different pulse durations. So again, longer pulses means more charge. So these were nice results. We show one here as well with the tissue placed over, so how we would want to conduct a chronic experiment. So this is fully open, just the skin, and then everything kind of on top of the device, and you just see a shift as you would expect. You have more tissue to penetrate through, so more brightness is needed to have the same effect. So that was good news for trying some chronic experiments, and that's exactly where we are at the moment. So we're in kind of iterations of device redesign, and hopefully we'll have more news on these wireless devices and the possibility in time soon. So for the optoelectronic ones, that's where I will leave it. If there's any other questions before moving on, we can take them. No? So then the other technique is called temporal interference. So this is completely non-invasive. This image is from Neil Grossman, who kind of retermed this temporal interference in 2017. It was shown before. This has the pairs of electrodes outside of the body and using different frequencies. So carrier frequencies that we call high frequency. For some of you guys, it's probably more like DC, but it's in the kilohertz range. And we have an offset frequency that, thanks to Wikipedia and the superposition principle, you can see nicely creates this envelope. So we would have something like 2000, 2010, and then we would get this envelope at 10 hertz. And this is nice because we have a hotspot that has the maximum of this effect. So whereas with something like, I'll go ahead here, so I'll show this for sciatic nerve experiment as well, but this has some modeling comparing TINS, which transcutaneous electrical nerve stimulation, which is quite well known, with this temporal interference. So whereas with TINS, you need to stimulate everything in the pathway, you have electrodes on the surface, and theoretically you can target something at depth, but it would be the least affected, the most affected tissue is here, and at some point you would just damage, basically burn the tissue. So with temporal interference, you can have a hot spot that is targeted on the nerve or biological target at depth, while the tissue in between is not affected or not stimulated. So this works by the overlapping of the electric fields and the creation of this envelope like you saw. So here we did some experiments to try and have a peripheral nerve stimulation example of this. This is with the mouse model, and again, this sciatic nerve stimulation where we're looking for the kick of the animal. So there's an animal video on the next slide. Here we have gold pins that are like this cartoon here that we place down and look for the alignment with the sciatic nerve. And then you can see it starts with a 0.5 hertz offset, and then we can move dynamically through the offset frequency, and you see it starts to have this kicking at 1 hertz, and then we'll move to 3000. So 3000 is the carrier frequency, 3002, 2 hertz offset, so you can see the kicking pickup, and then we go on to 5 hertz, I think, before giving his little muscles a break. So this was great. This is a demonstration of that working well with the peripheral nervous system. One thing that was challenging here are these gold pins are extremely rigid, and the leg is of course curved. So we had issues with trying to keep contact. Sometimes the one on the edge would just lose contact, or to align them in the first place. So we had then developed, so this is exactly the device I was passing around, an electrode grid that we could laminate onto the leg and then scan through the electrodes to look first for the alignment and to also keep good contact. So this is same thing, Perylene C substrate is the thin polymer, transparent polymer that we use, and gold thin film contacts, and then these P.PSS electrode coatings once again. And then it's just the same experiment, just to look for the alignment. Oh, it's somehow pixelated. Look for the alignment with the nerve and see that we have kicking. And we measured compound muscle action potential again, and had these demonstrations of that working well for the first time with peripheral nerves. So from here, there's a lot of applications. I'll show you one more example just quickly. So those are the two main kind of minimally and non-invasive forms of stimulation that we're looking into, and device development to go along with those. One thing that we think and we are starting to explore would be quite interesting is patient screening. So it's quite shocking to see the actual success rates of things like DBS and vagus nerve stimulation after the cost and pain of surgery, to have maybe something as low as 20-something% success on the other side, after the surgery. So it would be quite nice to screen the patients, know that they're responsive to this type of therapy, and then go through the surgery of the invasive one if needed. So we're looking into that first, again, with our collaborators with the mouse model, and in the beginnings of exploring vagus nerve stimulation and with these grids. Again, it's very small nerve and tough to target, so we're looking at some robust stimulation parameters first, and then we'll move towards looking at patient screening. Okay, so I'll show you one more example using this temporal interference for another application. The next slide does have the human surgery with vagus nerve. So here you can really see how big and invasive these devices are. So this is wrapped around the vagus nerve of a human. And some of these are the electrode contacts, and some are just the physical fixing of the device on the nerve. So again, that's the motivation for a lot of the materials and work that we're doing. So this is applied to other nerves as well. Some listed here. The one I'll show you is the hypoglossal nerve. And we've been looking into different, again, geometries, trying to find the most reliable layout and parameters. And so we've ended up with this cross design. So we have one frequency applied here and the other one with the offset like this. And this has so far been the best result for targeting the hypoglossal nerve. So what's the hypoglossal nerve? This has to do with obstructive sleep apnea. So normally when people are sleeping, we're breathing. If the tongue maybe starts to move back, we have the hypoglossal nerve to help us and keep the tongue tonus and push it back out so we don't block the pathway. With obstructive sleep apnea, this can fall back into the throat, and this is of course very dangerous, blocking the airway. So the current state-of-the-art solution for that is the CPAP machine, which you see here, and it's quite loud and uncomfortable. There's the infection risk because it's annoying to clean as well. For these reasons, there's poor compliance. In the other part of the photo, there's often a bed partner that also has to deal with this noise, and a lot of people don't like to use them, even if they do have some form of obstructive sleep apnea. So the other solution, if the case is extreme enough, is again to implant onto the nerve directly. So this is another, it has two sides, the hypoglossal nerve. This is a unilateral implant, so it's only on one side. And here you need the stimulation leads and the power supply and the sensor to know what's going on during sleeping. So we want to get around all that, of course, with temporal interference again. So I won't go into a lot of the details, just showing you that in the control, of course, nothing's happening, just the normal movement of the tongue or not if somebody has this disorder. If we stimulate on just one side, we would get a protrusion of the tongue on either one side or the other. And this can require larger amplitudes, but since there are two sides, we can target both of them and have this bilateral case where we would have a central protrusion, and we can also reduce the amplitude. So with these types of applications, I mean, the electrode is on the skin, and if you drive the voltage up, it stings or, feels weird. So we want to keep the amplitudes as low as possible while still having efficient stimulation. So the setup that we use looks something like this. This was just kind of the first trials using sports tape and connecting through the tape and trying to see what happens. But that works. We actually still use it for some tests. And here you see the frequencies that are used. I won't go a lot into that. It's the same concept, just the offset is a higher one in this case, this 50 hertz. And here you can see the actual stimulation happening. His tongue will protrude there. So we have it off for 2 seconds and on for half a second. And so it's, interesting. Yes? So here, like you saw before, it's usually in these hundreds of microamps per electrode. So this one, we have different results. Here I can show you already we have an extreme difference between men and women with the stimulation on and off. So there we've tried to drive higher, so it's always a question of just kind of asking the healthy volunteers, how it feels, and they can try. And we've tried it on ourselves also. It's an interesting feeling, but there is definitely some difference between men and women. And so sometimes we do push the currents higher if it's not affecting the person. Another thing that we can do is use higher carrier frequencies. So right now we've been kind of limited to about 8 kilohertz and down just because of the machines. But so I'll show you in a moment the group that's working a lot more on this. We collaborate on some of these projects, but yeah, they've been developing a little box, trying to develop like a smaller thing first of all. So I can also move here and go ahead and show you. This was the first setup just to see how it was to try sleeping with them. So these are called digitimers. They're each about that big and sound kind of like small airplanes. So we were just testing if it was even possible to sleep for some, because we wanted to go and do sleep trials in the clinic. So what we aim for is to have something, again, miniaturized that can be just kind of stuck under the chin. But so yeah, they're developing hopefully some electronics that give freedom of the signals we can apply, as well as have higher frequencies, because then you don't have this. So it's again the impedance at the skin and how fast you can apply the signal. And there we can push a bit higher and try to get effects where somebody's more resistant. But yeah, usually, let's say milliamp is starting to be the max. Yeah, so, and then here we were excited a bit ago to have this FDA designation of breakthrough device, so that was very cool. And we're in this stage still with trying to miniaturize and make some of these things more efficient. So then I have no idea how long I've been going, but I would just tell you quickly 2 more things. One is that we also work with medicinal leeches in the lab. So these don't require ethics, and we have used them for prototyping some devices as well. So they have just one single nerve down the body, and here you can dissect and essentially have access to the nerve. And so the next picture I'll show you is basically between 2 of the ganglia in the middle, where we have the most space. So here. And then we wrap, so this is the same device that we used for the vagus nerve stimulation in mice. Here we can wrap this around and do some testing with a less complicated model before moving on to other things. So here it's a readout just of movement. So this is the leech body here. We use some little colored markers and a scale bar so we can see how much it's moving. I'll just show you what it looks like. So it will kind of contract and stretch in the long direction. There it goes. And we can track these little dots and kind of compare between stimulation parameters. And this was done in parallel with those ones for the vagus nerve of the mouse. So this was a nice way to test things out. And look at a lot of those different parameters and patterns as well. Here you can't see anything except some of the light flashes. You can't see it all because of the capture rate, but then we could test some of those wireless devices as well. So this has the light source on top, out of the picture. And we got to use these leeches also in a publication we're very excited about from last year. So we had the chance to publish in Science. And this is moving one step kind of more integrated with the biology. So here, instead of creating devices and implanting and trying to have a good contact, and questions like what Steve asked, how good or what's the impedance match there at the electrode tissue. Here we want to polymerize these similar materials directly at the site that we're interested in within the tissue. So that's the environment of the biological tissue that kind of kickstarts this polymerization. And then we have conductive material really intimately in contact with that tissue. So we used what we typically call a just cocktail of different components. So we have a monomer and some things that make a gel as they cross-link during this process, and then some enzymes present in this cocktail as well. So HRP, horseradish peroxidase, and a redox enzyme. This is, in this work, was typically glucose oxidase and lactate oxidase. So what happens is depicted here with lactate oxidase as the example. Lactate in the environment, we create hydrogen peroxide, and then the way that this interacts with HRP, that kickstarts the polymerization, and then we create a polymer, as you see here. So this is, they turn blue as they become conductive and in the polymer state. So here we have just agarose gel to do this characterization. And then we moved on to other models, one of those being the leech. So they also have lactate present in their bodies. That's something we learned during this study. And so here we could inject this gel, see that it turns blue, and we use some of these electrodes to measure the conductivity and be able to quantify some of that. So here you just see the current before it's polymerized, and then after some time where we see visually that it's turning blue, then you can see we have a registerable current. This was also injected into the fins of zebrafish. And we also looked in with injections into the brain and heart, and to look at how the polymer developed there. So this is another thing that we're building on now, looking into how else we can use this. For example, epilepsy is a good example. There's lactate present in the environment when you have epileptic seizure, so that would be somewhere that you could try to create this type of polymer and have a very good contact with the site that's the source of the seizure. So these type of experiments and work is where we are now, building on that. And then the last I won't talk about, but we do quite a lot of transistor work as well, using again these materials that are mixed ionic and electronic conductors. So this can be, for the same reason, good with interacting for bioelectronic applications, within the added benefit that with transistors you can have amplification, of course. So that I won't go into, but we do have some work on that. With that, some of the acknowledgements. So these are some collaborators from Linköping University on this side. These guys too, but they've moved on to the Czech Republic. Here we have the team of Adam Williamson he has part of his work going on in the Czech Republic as well, and he's also affiliated with Linköping University. Maybe you recognize this guy from the first slides. He's also my husband that's been traveling around and exploring Europe with me. So his research team focuses a lot on temporal interference, as I mentioned. And then we have our collaborators, the Petter Olofsson team of Karolinska Institutet in Stockholm, who do a lot with vagus nerve stimulation. So they're experts in this field. This is the soft electronics group, of which I'm part, leading the flexible bioelectronics team. And then this is kind of the bigger animal that we're all a part of, the Laboratory of Organic Electronics. So 12 research groups, everything from theory and modeling to photonics, and then a lot of bioelectronic applications, and all based on these organic materials. And with that, I would thank you guys as well for joining today, and I'll take any questions if there are more.
You try the Utah array?
The Utah array, we haven't used them very much ourselves. So one of the guys that I had on the acknowledgement screen, he actually developed one with PDMS so that it would be like a flexible Utah array. So, but myself, I haven't used the actual Utah array for.
Utah array is very popular in the U.S.
Mm-hmm. Yes. So when you have, it's of course very rigid again, and it depends on how deep you want to penetrate, because there are often these more cortical regions. But it definitely is robust and has a lot of channels. So
when I was working with the fish farm, we try to stimulate the electrical fish using the electrodes. So one of the things we had is the problem that you don't want to inject charge into the fish, right? So you have to precisely control the amplitude versus the time. So make sure that the positive and negative power will match. So we have to use a precise digital to analog conversion to control the amplitude and time. Are you using similar things? I didn't see the control.
The setup, I guess I didn't show. You're correct. We usually use. Are you familiar with the INTAN system? So it's quite often used in just neuroscience in general. There's a few that are often used, and one of their systems is a stimulation recording combined system, and there you can access the electrodes individually. So where I was showing these patterns, and you can control within a range the current amplitudes and the time quite precisely. That's actually why we have, I don't know if you noticed, I was using often 266 microseconds, and that's just based on the limitation of the time steps that we can use. So this one was, so far for us, very useful. You can stimulate anything from some microamps up to, I believe, 2.5 milliamps. We haven't used the upper range so much. So for our applications, that's been fine. And where the normal setup isn't okay, then they have some analog connections that you can use as well for recording, for example. So
Because of any asymmetric mismatch, over the time it will accumulate.
yes.
Eventually you will depolarize the neuron.
Mm-hmm.
Have you ever seen the neuron depolarized?
I haven't. I've seen literature where they maybe even watch this effect over time intentionally, but with us, I mean, we try to keep. Yeah, I guess I didn't say that either. These pulses are usually charge balanced, so that you try to avoid this effect. So yeah, we just use in the software there, you can have exactly like I had it drawn, or the one where it's drawn out in the balancing phase, or some spacing in between. But yeah, it's definitely something that you have to watch for. Have you seen effects?
No, I heard about that. It's kind of horrible, but.
Yeah, exactly. Yes.
I'm curious, does your research require a lot of interface with School of Medicine or a biology department? Or?
Yeah, so that's what I guess I kind of alluded to at the beginning, is it is very interdisciplinary. So there's it's one of two things in this bigger group that I'm part of. He's recently brought in a neuroscientist to be part of the group, but we're mainly a material science and have a big clean room to work in these things. So I think it's a good move. I think it's useful, but it's kind of out of place being there initially. And he needs access anyways to the facilities that have animal models. So where I'm working directly, we can't do anything other than these leech experiments or worms or something similar like that. But we do definitely have biologists, which are very useful. There's a lot of biologists. We have a cell lab, so we need them especially there. And some of the kind of project collaborations, like this article I showed last, this is definitely a mixture of those material scientists, engineers, biologists. And then when it needs to be something in the animal models, then we have our collaborators, like I say, in Stockholm for the vagus nerve. In Linköping, there's a medical faculty. So there we can also work with rats and mice, some even with pigs. But yes, so it just kind of depends on the level. But it's really great to have within this group a mix of different people so that the small discussions can happen more efficiently.
I have another follow-up. So when you look at these devices and the regulatory process, we have FDA here. I'm sure you have an equivalent in many different places that you've been to. How do the regulations work? Here we keep hearing about FDA being very slow.
Yeah. Oh, FDA is, this kind of process is certainly slow if you want something that's actually like FDA approval. For most of these experiments, it's just based on the ethics applications. In there you can apply to try new materials, but for the human ones, then it can be more challenging. Yeah, we can't just take these optoelectronic devices and try them on humans. That will take quite a lot of time, or even this P.PSS, because the way that the polymer is made can have toxic components to create the polymerization, and even though they should be out, I don't know if this one can get FDA approval in the end. So it's been used in humans, but only in parts of the brain that will be resected anyhow. So yeah, FDA approval is certainly a big challenge everywhere.
So Sweden is an equivalent, France probably has an equivalent. Are their procedures equally time-consuming, or?
Yes, everything that I know of is a challenge if you're trying to reach that level. Yep. Yes.
What about manufacturing process to train those low electrodes or any? Is there also manufacturing?
So we have a clean room there and use a lot of photolithography for the devices that I've been showing. So there we can pattern down to a few micrometers for the line size or the electrodes or whatever. We have a lot of printing facilities as well. And within, again, this soft electronics group, they have developed a lot of laser processes too. So to process the material and then ablate the parts that they don't want. And this is becoming quite good with the resolution too, so maybe down to some 10s or 50 micrometers. But most of the ones that I've shown you that are these small patterns is all based on photolithography, and we have class 10,000 and class 1,000 to carry out those processes. And I didn't pass it around, but if you guys want to come up, I actually have one of the stretchable soft electronics devices too. So these are quite interesting for wrapping around the nerve as well. If I can get it out of here. So yeah, this is not my main focus, but within the group, these can stretch quite a lot and keep their conductivity. So this is also great for nerve interfaces or biological interfaces. Yes?
Do you look at waveform diversity in terms of achieving certain effects for certain therapeutic purposes?
So for the optoelectronic devices, for example, we essentially are dependent on how the device has this transient in the photovoltage and photocurrent. We can do some things to modify that and change the shape of the resulting curve. But for the temporal interference, then there is a lot that we look at. So it can be these sine waves like you looked at, or pulses, or square waves, and that's a big part of what's being explored to try and see how the effects are and improvements on these things like the gender dependency. Okay.
Thank you very much.
No, thank you.
There's still